Okay, we're going to move on to our second speaker. Second speaker is Dr. Matthew Gomez. Matthew's an alumnus of the SSGF program, earned his PhD at University of Michigan in nuclear engineering and radiological sciences, 2011. He's currently a PI at Sandia National Laboratories in New Mexico, and is going to talk to us today about magnetized liner inertial fusion.
All right, thanks. So for those of you who were here last year, Ryan McBride talked a little bit about this fusion concept that we're trying at Sandia. It's an inertial confinement fusion concept. So I know that that's not really the area of everybody. But hopefully, since you guys saw NIF yesterday, you have some ideas about what they're doing there. And I'm going to try and explain this subtly different concept and then try and describe the differences and put it in perspective relative to what you may have seen. So much like all of the work that gets done on these big facilities, there are tons of people involved. These are most of the other scientists that were involved in this research in particular, but there's probably 100 other people that could have been on the list if there was space. So just a summary of these experiments and what we've seen so far. These are very new. We've done about 5 total experiments on this, and first one starting at the very end of last year. So these magnetized liner inertial fusion concepts, we were able to successfully demonstrate thermonuclear neutron generation in a DD plasma. So that's deuterium on deuterium. And the yields are maybe not quite the same as what you might see on NIF, but I'll try and address that. But it is a reasonable number, and it's somewhat consistent with the simulation, so we're pretty happy with that. We're demonstrating fusion-relevant stagnation temperatures, which for the velocity of this implosion is actually, it hasn't been done before. And we demonstrated a relatively stable pinch with a narrow stagnation column. That's this image shown here. Effectively, you have a 6 or 7 millimeter tall and 100 micron wide column of plasma. That's your final stagnation. So that's your source of your neutrons. And also one of the really exciting demonstrations of these experiments was successful magnetic flux compression, which is important for this concept to actually function. So this talk was actually originally given at the International Conference on Plasma Science, and in that audience, typically people have a pretty good idea of high energy density science. I added in some extra slides and I will probably try and focus mostly on that just to define what MagLIF is, and then maybe go a little bit lighter on some of the other analysis. But magnetized liner inertial fusion is the ICF concept that we're trying to use, or that we're testing on Z at this point. The idea is that you can apply a magnetic field to a plasma to inhibit thermal conduction, and as a result, if you heat that plasma at some early time, it will stay relatively hot. As you compress it, it'll continue to heat, and then you can achieve relatively high fusion relevant temperatures without having to set up 4 shocks that come in at exactly the same time, or without having to converge to an unreasonably high convergence ratio. So the first stage is applying a magnetic field to a target. So you have a liner shown here in dark blue. It's made out of beryllium. The gas inside here is deuterium gas. So yesterday we had a couple talks where we talked about some fusion concepts, and one of the reactions that you can have is deuterium on deuterium produces a neutron and a helium-3, or you can also produce a triton and a proton. So those are the 2 branches of that reaction that you can get. So we're looking for that reaction. There's also this deuterium on tritium reaction, which can occur. And since we're producing tritium, some of that can react with the deuterium that's already in there and produce an alpha particle and a neutron with a higher energy. So we apply this magnetic field, which runs axially in this cylinder. And that's important because we're going to inhibit radial transport of the heat, but we're not going to inhibit it along the axis. But that's okay because this ends up being a relatively long and skinny target, so the heat flux out of the axis, there's actually a relatively small area for that to go out of, whereas the heat flux to the wall is comparatively large. So this is a convenient geometry. For those of you who are familiar with the experiments that have been done at Omega, which are similar to those done at NIF, they actually recently applied effectively an axial magnetic field to their targets as well and showed that you could improve the fusion output of the target, but only by, say, 50% or something like that, because in that case you have an axial magnetic field and a spherical implosion. So you don't actually gain the same benefits that you do from a cylindrical geometry, which is more complementary to the axial field. So you're running a current on the outside of this target, which creates this azimuthal magnetic field. That creates a J cross B force, which causes this liner to start to implode. But just as you're applying that current and starting the process, you fire a laser into the top of the target and heat up this fuel here. And you heat that up to hundreds of eV. So our target goal is to get into the keV temperature range, sort of few keV to eventually 10 keV. And if you start off at hundreds of eV, then at convergence ratios of, say, 20 or 30, which are pretty believable, you can achieve temperatures in that range. If we were to start this off at, say, room temperature, which is fractions of an eV, the volumetric compression of this would not get us anywhere near relevant temperatures. So the laser is actually a really critical component of this. So again, the magnetic field, which is axially located in this target, prevents this heat from passing into this liner here, but it can still escape axially. So as the current increases, this liner begins to implode faster and faster, and then over the course of about 100 nanoseconds, which is again long compared to, say, a NIF implosion, which is tens of nanoseconds at most, you heat and compress the fuel into this hot plasma on axis. So the axial magnetic field that you have within this liner, since it's the plasma's conducting and the liner's conducting, is actually entrained within it. So as you compress it, you go from something that starts off at an initial magnetic field of, say, 10 Tesla, and then you multiply it basically by your convergence ratio squared. So if you converge by a factor of, say, 30, then you go up by a factor of 900. So you're basically, you can go from 10 Tesla up to almost 10 kilotesla by imploding these liners. And that's great because the magnetic fields that you're achieving at that point are actually sufficient to make the Larmor radius smaller than the radius of the plasma. So any tritons, well, the Larmor radius for tritons, and equivalently alphas, because they're very similar, will be confined within this plasma as long as the Larmor radius is relatively small compared to the stagnation radius. So this is a movie showing a simulation of just generally the concept of what's happening. So this may help you get a better idea. You're running a current on the outside of this and causing it to move. This liner here is imploding. And as it starts to implode, you have a laser that comes in and heats the gas. Then the liner continues to implode, increasing the temperature to something on the order of several keV. So the experimental setup for these experiments that we've been doing at Sandia required a lot of work because this is not something that we typically fired. For those of you who are familiar with the machine, we do a lot of Z-pinch work, which was wire array Z-pinches, radiating wires. This is looking at solid cylindrical liners, so that's a little bit different. It has this magnetic fields coils that have to be implemented on the machine, as well as the laser being incorporated into the target implosion. So basically, this is a process where the first paper defining this concept came out in around 2010, and here we are 4 years later, and we've only done a couple of these experiments. And that's not to say that we haven't been doing things along the way. Effectively, we've done a series of laser-only experiments where we injected a laser into the target to look at what the heating of the plasma was. We applied a magnetic field to the exterior of the target to look at how that affected the implosion and current delivery to the target. We looked at liner stability for many years, trying to determine if the magneto-inertial instability, which develops on the outside of the liner, would end up shredding it. So there's some trade-off in what the thickness of the liner has to be in order to mitigate that problem. And we had to modify the power flow here so that the target could be centered within the magnets. Otherwise, the magnetic field wouldn't match the axial geometry that we're trying to implement. So to date, we've done a total of 5 integrated experiments. For context, I think NIF has been up and running for about 5 years. So however, whatever fraction of experiments they've done, it may be hundreds of experiments that they've done to look at, to evaluate the high foot concept, but then maybe like the low foot concept. The high foot concept that has come up recently, they've kind of looked at a few things, and that's really sort of taken off. And what we're hoping is that we're looking at these things and hoping that this is an interesting concept that'll kind of follow a similar trajectory. So I think that a lot of this stuff is probably not really that necessary, but for you guys, just to give you an idea of what the scale of these are, again, the target's about a centimeter tall, and it's around 1/2 centimeter wide, so it's a relatively small thing. And effectively, we've used simulations and all these experiments that we've been doing over the years to modify certain things about the target to try and improve them to eliminate some of these instabilities that can come up. So more information generally about how the experiments work. The magnetic field that's being applied to these experiments happens on a relatively long time scale. So this is basically a several millisecond rise time on the magnetic field. And that's required because the target is actually made out of metal. It's conducting. So in order to get the magnetic field to diffuse through that metal, you have to have it happen on a relatively long time scale, or you can cause buckling and stresses that you're not looking for. The time of the experiment is actually quite short, so we're basically just right at the peak of that. The experiment itself, this is the rise time, or the current of the Z machine. So we have about 20 million amps over about 100 nanosecond rise time. This red block shows roughly what the liner trajectory looks like. So in this case, you have something that's relatively thick, which provides us good stability while it's imploding, and it moves at a relatively slow rate. So again, this is, it may not be obvious that it's slow, but this is a 70 kilometer per second implosion, which it sounds fast, but compared to, say, a NIF implosion, which might happen on the 300 plus kilometer per second, there's actually a pretty different regime that you're operating in. So the temperature that you can achieve goes something like the velocity to some relatively high number. So the fact that we're down by a factor of 4 or so in velocity actually is a factor of many in what the total temperature you can achieve. And that's part of the reason why we have to have this laser to put us on that higher initial adiabat, so we can achieve the temperatures we're interested in. So the laser that we're using is about a 2 kilojoule laser with a half kilojoule pre-pulse. It's a terawatt class laser. And the idea of this pre-pulse is effectively, on this slide I showed, there's a window on the top that holds in the gas. Well, you'd like the laser to come in and heat the gas, but it'll interact with that window as well. So you have this little pulse of laser energy that you hit that window with first that causes it to kind of rarefy somewhat so that maybe more of the laser energy will get through at a later time. So moving on to the actual experiments, I was lucky enough to be involved in these kind of from the beginning of the integrated experiments. And effectively, we did a series of experiments where we had the liner, no magnetic field, no laser, and just looked at what happened. And we got basically the lower limit of what we could measure in the way of neutrons, which is around 10 to the 9. We added the magnetic field and basically didn't see much. There's a subtle but not significant improvement in that. And then when we added the laser as well, you can see that on 3 of the experiments, fantastic, it increased by several orders of magnitude, and we were very elated to see that. On one of the experiments, not really sure what happened. It was the very first time we implemented all these things. It's a relatively complicated system, and it's still not really clear why that experiment didn't work and the other ones did. But we've yet to be able to reproduce that result. So we're somewhat confident that it's related to maybe an alignment error in one of the, either the laser or something related to how the target was being implemented. So using neutron time of flight, which is a diagnostic that measures the time at which neutrons hit a detector, which gives you some information about the energy of the neutrons, because basically if they're emitted with some initial velocity, they'll be separated in time based on what that initial energy that they were born with was. So looking at the deuterium-deuterium interaction that produces this 2.45 MeV neutron peak, you can see that we have actually a relatively Gaussian neutron spectrum with some low-end scattering issues, which actually looks like it comes from scattering off the beryllium liner, which may be an effective diagnostic for what the rho R of the liner actually is. But you can fit this profile, and then it's a relatively common technique for finding out what the ion temperature of the plasma is. So in these experiments, the ion temperatures run the order of 2 to 2.5 kilovolts, which is on the low end, but within the realm of interesting plasma temperatures for fusion. So we also used a high-energy X-ray spectrometer to look at emission from the plasma. And basically, this is a plot of photon energy as a function of X-ray yield for 2 different cases. So if you apply both the laser and the magnetic field, then you can get a temperature that's on the order of 3 kilovolts. And if you don't include them, if you only apply the magnetic field and don't include the laser, then there's no reason why the plasma should get any hotter than just a normal implosion. So it stays at right around kilovolt. And it should be noted that this kilovolt is roughly the threshold of this measurement. So this is really sort of an upper bound on what that value is. And so for clarity, the temperature is being calculated based on the slope of the continuum in this X-ray spectrum. So one of the nice things about this series of 5 or so integrated experiments plus a few other null experiments over the last year is that everything trends as you might expect. So for relatively low electron temperatures, we have low yields, and we don't observe ion temperature, which can only be measured if we had neutrons. And as we increase, when we apply the laser, the electron and ion temperatures both go up and become measurable. And we also see a DD yield. And on those experiments, we see this secondary reaction where the tritons that are created in this plasma are actually trapped by the magnetic field and interact further. And so that's an indication that we are undergoing this flux compression that we were hoping would be achieved. So there's a narrow X-ray burst that comes out of these targets, and that X-ray burst basically coincides with where the bang time for the neutrons is from the neutron time of flight detectors. And this is important because we actually see on experiments that there is no yield. There is also an X-ray signature, but the X-ray signature has a lower photon energy, so it's colder, and it happens at a later time. So this is a nice consistency check to say that if we know which peak we're looking at, we can definitely identify it to be a part of the neutron-producing plasma. So expanding that further, if you take X-ray images of the plasma at the time at which you have this peak, you basically see a relatively narrow stagnation column that's occurring where you might expect it on the axis of the target. So that column shows up only for a short period of time, roughly 2 nanoseconds, which is consistent, again, with what the X-ray diodes would predict. And this stagnation column is interesting because it's at the resolution limit of our instrument, which is 150 microns. So you can imagine we're starting off with something that's about 4.5 millimeters ID, and we're getting down to something that's potentially sub 150 microns. So you're talking about a compression ratio, convergence ratio of about 30, which is pretty high, but that's actually a pretty good sign for these experiments, because in the future we intend to have targets where they only converge about a factor of 20 because the laser energy is a little bit higher, and so the back pressure from the plasma is greater. So this is just kind of a nice check on how these targets are functioning. So as I mentioned, there's also other X-ray signatures that come from all of these plasmas, so it's important to be able to weed out what the difference is between these two. So looking with a lower energy filter on that same pinhole imaging camera, you can see this emission from what appears to be the outside of the liner coming in, stagnating, and then bouncing. That corresponds with this late time X-ray peak. When we first saw this peak, before we had actually done any of the other experiments, we were a little concerned we wouldn't be able to identify the difference between the two. So we did a series of experiments where in the one case we filtered for high energy photons only. That's this black trace here. And that's on a fully integrated shot with the laser and the magnetic field. When we did the same exact measurement, or same experiment, changed the filtration so that we were looking for lower energy stuff, we see this red trace. And then a third experiment where we removed the laser and kept that same low energy filtration on the diodes, we see this blue trace. So you can see there's actually very good consistency between these where these peaks show up, what time they come, and what they correspond to. So we know that this is a low energy, this is high energy, and that this only occurs in the experiments where you have the laser and the magnetic field to help your plasma get to these higher temperatures. So we also have some self-emission imaging diagnostics that we use. It's basically a spherical X-ray crystal that you use to take emission from the target and image it onto a camera. So you can isolate particular photon energies using this technique. So that's where this image of the full height of the pinch comes from. This is a time-integrated image, so it's a little bit different than those other pictures, but effectively, since we know that those are only occurring over a short period of time of roughly less than 2 nanoseconds, this is essentially a 2 nanosecond snapshot of the emission from the plasma. So again, this has a little bit better resolution than the previous measurements, but it's about 60 microns is the minimum resolution. And in this case, we're seeing something that is maybe as small as 60 microns, which, as I said before, given convergence ratios, this is actually getting to be quite large. We don't necessarily believe that that's the convergence ratio of the entire fuel region, but it is the size of the hot fuel that we're seeing in this plasma. So taking those values and establishing a rough volume of the fuel, and knowing that the emission is only occurring for about 1 to 2 nanoseconds, getting a rough stagnation density estimation from the X-ray spectroscopy, and a stagnation temperature range that you get from the ion temperatures from the NTOF and the X-ray temperatures to get the electron temperature, you can kind of give a bound on what you think that the reaction cross-section should be for this fusion plasma. And then from that, you can figure out basically what you think would be a theoretically calculated yield for a thermonuclear plasma that has all these conditions. And that's shown here, which is 2 × 10⁻11 to as high as maybe 8 × 10⁻13. So the measured yields we had on these experiments are within that range, and 5 × 10⁻11 to about 2 × 10⁻12. So this is just a good consistency check, because in a lot of Z-pinch plasmas previously, people have postulated that the neutron generation could be from beam-target interactions. So you imagine you have, sure. So, well, we'll just skip on just really quickly to talk about where we're going with these experiments. So as I mentioned, there's a laser that's coming into the top of the target, and the intention is to have a plasma that you heat with this laser. The more heat you can put in at that time, the more effective you can be at producing neutrons. So in these experiments, these are the yields that we had, and this is a simulation of what you might expect for reasonable performance as a function of laser energy. We don't have a direct measurement on these experiments of what the exact laser energy put into the target was, but on the equivalent laser-only experiments that we did previously, we established that we were getting somewhere between about 100 and 200 joules of laser energy in, so we're only about 10% efficient through that window. We've been recently doing some experiments to improve that, and we've gotten as much as 2 kilojoules into the target in these laser-only experiments. And the idea is that, assuming the simulations are correct, you could imagine this increasing by 1 to 2 orders of magnitude when we test that out on the actual experiments, which we intend to do in September. This is just kind of a comparison of our simulation to our experiment and what the observed parameters are versus the simulation. Basically, in all cases, it matches what we intend, but I won't talk about that too much. The future for these experiments, we just recently finished upgrading the laser to 4 kilojoules, and that's what enables this 2 kilojoule transmission through the window. We're working on an additional upgrade to get to over 6 kilojoules by the start of next year. We're also looking into smoothing of the laser beam to improve this transmission. So basically, we're relying on the laser, the magnetic field, and the drive current to form this plasma that we're looking at. And so we're slowly incrementing up all of those things, the target being that we would like to be able to achieve reasonable fusion yield, an increase of a factor of a couple orders of magnitude over the next 2 years. So with that, I'll take questions.